Alright, let's start. Zombie stars. Most stars, when they explode, are gone forever. But a small class of white dwarfs manages something that should be impossible, surviving their own thermonuclear detonation. These are called zombie stars, the predicted survivors of a peculiar class of explosion known as a Type Iax supernova. In a standard white dwarf explosion, the entire star is incinerated in a fraction of a second. In a Type Iax event, the detonation burns through only part of the star, leaving behind a bloated, destabilized remnant still smoldering from within. Scientists estimate that Type Iax events may account for roughly 30% of all white dwarf explosions, making zombie stars potentially far more common than anyone expected. The surviving star would be dim, puffed up, and moving through the galaxy at high speed, a wounded object carrying the chemical scars of an incomplete death. What makes them genuinely unsettling is the implication. Stellar death is not always final. Some stars begin dying and then simply don't finish. Current models suggest a zombie star might eventually detonate a second time, completing the process its first explosion could not. For now, they remain one of the strangest predicted objects in stellar physics, stars that crossed the threshold of destruction and came back. Thorne-Zytkow objects. In 1975, astrophysicists Kip Thorne and Anna Zytkow proposed something that sounds less like science and more like science fiction. A star with another star hidden inside it. A Thorne-Zytkow object forms when a neutron star, the dense remnant of a supernova, spirals into the core of a red supergiant and takes up residence there, replacing the star's nuclear burning heart with a city-sized ball of compressed neutrons. From the outside, the object looks like an ordinary red supergiant, but its core is not a furnace of fusing hydrogen or helium. It is a neutron star, one of the densest objects in the universe, quietly powering the giant star's luminosity through a completely different mechanism. The chemical fingerprint of a Thorne-Zytkow object should be distinctive, showing unusual abundances of elements like rubidium, lithium, and molybdenum. One candidate, a star designated HV 2112 in the Small Magellanic Cloud, has attracted significant attention, though its classification remains debated. It may be an unusual asymptotic giant branch star instead. If genuine Thorne-Zytkow objects exist in large numbers, they could be quietly reshaping the chemical composition of their host galaxies, enriching the interstellar medium in ways no standard stellar model predicts. Blue straggler stars. In an old stellar cluster, every star formed from the same cloud of gas at roughly the same time. As billions of years pass, the most massive stars exhaust their fuel and die, leaving behind only the slower burning, cooler, dimmer stars that remain. But scattered through some clusters are stars that break this rule. Blue, bright, and hot, behaving as though they are far younger than everything around them. These are blue straggler stars, and their existence is a paradox written in light. They cannot be young. The cluster sealed its star-forming material away billions of years ago. The explanation requires a kind of stellar theft. Blue stragglers are thought to have stolen mass from a nearby companion star, or merged with one entirely, effectively restarting their internal clock. The infusion of fresh hydrogen pushes them back toward the hotter, bluer part of the stellar sequence, not because they are newborn, but because they have been rebuilt. In globular clusters, dozens of blue stragglers can be found congregating near the center, where stellar encounters are most frequent. They are rejuvenated stars, wearing borrowed youth in plain sight, standing out like a bright flame in a dimming room. Their existence reminds us that a star's fate is not always determined by what it was born with. Sometimes it is determined by who it meets. Magnetars. A neutron star already occupies a category of extremity that is difficult to fully absorb. The mass of the sun compressed into a sphere roughly 20 kilometers across, spinning hundreds of times per second. But among neutron stars, a small subset exists in a register so violent it belongs in a different category entirely. Magnetars carry magnetic fields reaching 10 to the power of 15 Gauss, trillions of times stronger than Earth's, and the most powerful magnetic fields confirmed anywhere in the known universe. At these intensities, the star's own crust cannot hold together. Magnetic stress cracks the surface in events called starquakes, and each fracture releases a burst of X-rays and gamma rays that can be detected across the entire galaxy. In 0.2 of a second, A single Magnetar giant flare can release as much energy as our sun will emit across 100,000 years. A 2004 event from a Magnetar designated SGR 1806-20, located 50,000 light-years away, was energetic enough to measurably ionize Earth's upper atmosphere, the equivalent of a cosmic explosion on the other side of the galaxy, leaving a physical mark on our own world. Only around 30 Magnetars are known in the Milky Way, and they remain active for only about 10,000 years before their extraordinary fields begin to decay. Brief, violent, and incomprehensible in scale. Hypervelocity stars. Every star in the Milky Way follows a gravitational path around the galactic center, bound to the galaxy by the same invisible architecture that keeps planets in orbit around a sun. But some stars have been ejected from that architecture entirely. Hypervelocity stars travel through the galaxy at speeds of 500 to over 1,000 kilometers per second, compared to the sun's orbital speed of roughly 220 kilometers per second, moving so fast that the galaxy's gravity cannot hold them. They are permanent escapees. The most widely accepted explanation involves the supermassive black hole at the center of the galaxy. When a binary star system passes too close, gravity tears the pair apart. One star is captured into a close orbit around the black hole. The other is flung outward at extraordinary speed, a gravitational slingshot launched by one of the most massive objects in existence. Several dozen hypervelocity stars have been confirmed, and some will reach intergalactic space within tens of millions of years, drifting forever through the void between galaxies. They are stars that began their lives inside the Milky Way and will end them in the emptiness between galaxies, cast out by the same black hole that anchors the galaxy they were born in. Symbiotic stars. Some of the strangest stellar behavior does not require an exotic object, only proximity. In a symbiotic star system, a cool bloated giant and a tiny white dwarf orbit each other closely enough that the giant's stellar wind streams continuously onto the white dwarf's surface, fueling an ongoing chemical drama across the pair. The mismatch between the two objects could not be more extreme. The giant is vast, cool, and luminous in infrared light. The white dwarf is small, scorching hot, and radiates fiercely in ultraviolet and X-rays. Together, they produce radiation across a span of the electromagnetic spectrum that no single star could generate alone. As a hydrogen-rich material accumulates on the white dwarf, it periodically ignites in nova-like explosions, briefly flaring thousands of times brighter before settling back into its parasitic feeding routine. Some symbiotic systems may be rehearsing for something even more dramatic, slowly building toward conditions that could trigger a full Type Ia supernova. Known examples include RS Ophiuchi, which has erupted multiple times in recorded history, and CH Cygni. There are roughly 200 known symbiotic systems, each one a binary partnership where the chemistry of their interaction writes itself across the entire electromagnetic spectrum. Rapidly oscillating AP stars. Among the chemically peculiar A-type stars, a subset does something that most stars are incapable of. They ring. Rapidly oscillating AP stars, known as ρAP stars, pulsate in acoustic oscillations with periods as short as 4 minutes and as long as 21 minutes, vibrating like spherical bells at frequencies dictated by the physics of their interiors. But the pulsations are only half the story. These stars also possess magnetic fields strong enough to sort the periodic table across their own surfaces. Elements like europium, gadolinium, and praseodymium, rare earth elements, accumulate in patches at the magnetic poles, reaching concentrations tens of thousands of times greater than in the sun. One hemisphere of the star can be chemically unlike the other, as if two entirely different stellar compositions have been painted onto a single object by an invisible magnetic brush. The concentration process, known as atomic diffusion, relies on the interplay between gravity pulling heavy atoms down and radiation pressure pushing them up, creating a separation of elements that no amount of stellar mixing can undo. About 60 of these objects are known. Each one is a star whose surface is simultaneously a geochemical map and a musical instrument, playing inaudible notes while displaying chemistry that should not exist anywhere in nature. Black widow pulsars. Millisecond pulsars, neutron stars recycled to extraordinary spin rates by accreting mass from a companion star, are among the most precisely timed objects in the universe. But in a subset of these systems, the pulsar has turned on the very companion that gave it new life. Black widow pulsars orbit a low-mass companion star so tightly that their intense radiation and particle wind ablate the companion's outer layers, slowly evaporating it into space. The companion, already depleted from years of donating mass, is now being destroyed by the object it created. Some companions have been reduced to masses smaller than a large planet, the eroded remnant of a once normal star. The first confirmed Black Widow pulsar, PSRB 1957+20, was discovered in 1988 and spins over 600 times per second, completing a full orbit with its companion in only 9 hours. The irony embedded in these systems is hard to overstate. A neutron star is resurrected by mass transfer, spun up to extraordinary speed, and then uses that very energy to disintegrate its benefactor. Left alone long enough, the pulsar may eventually complete the erasure entirely, an isolated millisecond pulsar with no companion remaining, its history of cosmic ingratitude written only in its impossible spin rate. Quasi stars. The early universe faced a problem that standard stellar physics cannot solve. Observations suggest that supermassive black holes, some containing billions of solar masses, were already fully formed less than 1 billion years after the Big Bang. Normal black holes, growing by accreting gas at theoretical maximum rates, cannot reach those masses in that time. One proposed solution involves a class of object that may never be directly observed, the quasi-star. According to theoretical models, a collapsing gas cloud in the early universe could form a black hole before its outer envelope disperses. That black hole would then grow by consuming surrounding gas, and the energy released from accretion would power an outer shell that glows like an enormous star. Not from nuclear fusion, but from a black hole engine buried inside. Scientists believe quasi-stars could theoretically have been hundreds of times the radius of ordinary stars, potentially millions of times more luminous than the sun, and capable of seeding black holes that would go on to become the supermassive objects we observe at the centers of galaxies today. No quasi-star has been confirmed. They exist entirely in the mathematics of early universe models, but if they formed, they represent a category of stellar object unlike any other, stars powered not by the burning of atoms, but by the gravity of their own destruction. Canum Venaticorum stars. 2 white dwarfs can orbit each other. At typical separations, this is unremarkable. But some white dwarf binaries have spiraled so close together, drawn inward by gravitational wave emission, that their orbital periods have shrunk to minutes. Canum Venaticorum stars, named for their prototype, are binary systems in which 2 white dwarfs orbit so tightly that one is physically transferring helium-rich material onto the other in a continuous stream. AMCVN itself completes an orbit every 17 minutes. The most extreme known example, HM Cancri, orbits in approximately 5 minutes and 21 seconds, the shortest orbital period of any confirmed binary system in the universe. At these separations, the stars are so close that the accreting white dwarf's gravity raises enormous tidal distortions on its companion. The helium accretion stream glows, the system pulses, and all the while, the 2 objects continue to spiral closer. AMCVN systems are among the predicted primary sources for space-based gravitational wave detectors like the planned LISA mission. Their tight orbits produce ripples in spacetime strong enough that these compact systems may be the first individually resolved gravitational wave sources from an entirely new class of detector. The most compact stellar pairs in the galaxy will become a form of cosmic music visible only to instruments that don't yet exist. Trubiski's star. A star's spectrum is its chemical autobiography. Every element present in the atmosphere leaves a precise signature at a specific wavelength of light. Astronomers have been reading these signatures for over a century. Then in 1961, Polish-Australian astronomer Antoni Trubiski pointed a telescope at an unremarkable-looking star in Centaurus and found a spectrum that defied interpretation. The star, formerly designated HD 101065, showed lines for extraordinarily rare elements in concentrations that had no precedent. More troubling, subsequent analysis suggested signatures consistent with elements so short-lived that they should not exist in detectable quantities on any stellar surface. Isotopes of actinides with half-lives measured in years, days, or less. Under normal conditions, these atoms decay so rapidly that any formed in the star's history would have vanished long before light could carry their signature to a telescope. Various explanations have been proposed: unusual nuclear physics, continuous in situ synthesis, or the diffusion of long-lived isotopes that produce similar spectral features. None has achieved consensus. Trubiski's star remains the most chemically inexplicable star known, a single object whose spectrum challenges the established understanding of what a stellar atmosphere can contain. Decades of analysis have narrowed the mystery without resolving it, and the spectrum continues to resist every clean explanation offered to it. Boyajian star. In most variable stars, brightness dips follow predictable schedules: an orbiting planet, a pulsating interior, an eclipsing binary companion. When citizen scientists combing through data from the Kepler Space Telescope flagged a star in the constellation Cygnus for unusual behavior, astronomers expected a simple explanation. They did not find one. KIC 846-852, now widely known as Boyajian star or Tabby's star, it dims in completely irregular patterns at unpredictable times, by amounts ranging from fractions of a percent to over 22% of its total brightness. The shapes of the dimming events are asymmetric and complex, inconsistent with any simple transiting body. Over longer timescales, the star appears to have been gradually fading for at least a century. The most rational current hypothesis involves swarms of dust or disintegrating cometary material drifting in front of the star in irregular clouds. The wavelength dependence of the dimming, deeper at shorter wavelengths, supports dust rather than any solid object, but a complete explanation for both the short-term dips and the long-term secular dimming together remains elusive. The star became briefly famous for a megastructure hypothesis that the scientific community does not seriously support. What it genuinely represents, stripped of speculation, is perhaps more interesting: a perfectly ordinary F-type star that nature has arranged to behave in a way that no one predicted and no one has yet fully explained. Why dwarf stars? The coldest objects that can be called stars occupy a category so extreme that the word star begins to feel misapplied. Why dwarfs are the coldest confirmed class of brown dwarf, failed stars that never ignited sustained hydrogen fusion, and their surface temperatures can drop below the boiling point of water, into ranges comparable to a warm afternoon on Earth. The coldest confirmed white dwarf, WISE 0855-5-0714, has a surface temperature of approximately minus 23 degrees Celsius, colder than the human body, colder than most kitchen ovens in reverse, and colder than some places on Earth during winter. These objects are entirely invisible to optical telescopes. They glow only in the deep infrared, detectable only because their thermal radiation leaks faintly into wavelengths our eyes cannot process. Their atmospheres are predicted to contain water ice clouds and possibly rain, precipitation of the same compound that falls on Earth, occurring in the atmosphere of an object that was born from the same gravitational collapse process that made the Sun. Why dwarfs do not simply blur the line between star and planet, they dissolve it. They are proof that the universe builds a continuous spectrum from stellar furnace to frozen world with no sharp edge between, and that somewhere in that spectrum, the categories we use to describe the cosmos quietly become inadequate. Population 3 stars. Everything in the universe that is not hydrogen or helium was made in a star. Every carbon atom, every iron nucleus, every trace of oxygen and calcium and gold and uranium, all of it was forged in stellar interiors or scattered by stellar explosions. But hydrogen and helium existed first before any stars at all, created in the first minutes after the Big Bang. The first generation of stars to form from that primordial gas is called Population 3, and they have never been directly observed. Because there were no heavy elements to help cool their collapsing gas clouds, Population 3 stars likely formed enormous, possibly hundreds of solar masses or more, and burned through their fuel in only 1 to 3 million years, a cosmic instant. When they exploded, they created and distributed the first heavy elements in the universe, seeding the gas clouds that would eventually form the next generation of stars, and the generation after that, and eventually the Sun, and Earth, and every living thing on it. No Population 3 star survives. None has ever been caught in the act of shining. The James Webb Space Telescope is searching for their indirect signatures in the spectra of early galaxies, and may have already begun to detect faint traces of their influence. The most important stars that ever existed left the universe entirely before anything could witness them. Luminous blue variables. A star has a theoretical brightness limit. At some luminosity, the radiation pressure pushing outward becomes so intense that it overwhelms gravity pulling inward, and the outer layers are blown away. This limit, known as the Eddington luminosity, represents a hard ceiling above which a star should not be able to sustain itself. Luminous blue variables occasionally ignore it. These massive, unstable hot stars periodically undergo eruptions that briefly push them beyond the Eddington threshold, temporarily producing more radiation than their own gravity should permit them to sustain. And yet, they survive. The most famous example is Eta Carinae. During the 1840s, Eta Carinae underwent a giant eruption that made it the second brightest star in Earth's night sky. Not because it exploded as a supernova, but because it briefly released energy in visible light comparable to what most supernovae produce, while the star itself remained intact. The material ejected during that event now forms the Homunculus Nebula, two expanding lobes of gas and dust stretching further than our entire solar system, and still expanding today at over 600 kilometers per second. Eta Carinae currently shines at roughly 5 million times the luminosity of the Sun, balanced at an edge that physics says it should not be able to maintain. What luminous blue variables demonstrate is that the theoretical limits of stellar physics are not firm walls. They are thresholds that nature, given sufficient mass and instability, can briefly and spectacularly exceed. The universe does not sort its stars into neat categories. It builds objects that sit between definitions: half star, half planet, half dead, half impossible. The strangest stars are not anomalies. They are reminders that every classification we use is a tool we invented, and the cosmos has never agreed to follow it. From the first light of stars that no telescope will ever see, to objects still shining beyond every limit we understand, the strange ones are always pointing at something we haven't figured out yet. If you want to see more, click the video on screen now.